All right, today we are going small. No, I mean smaller than microscopic. We're diving into nanomedicine, a field that's totally rewriting the rules for how we diagnose and treat diseases, all by working at the scale of individual atoms. Let's see how it works. Just think about that for a second. Instead of cooking up drugs in a lab and just kind of hoping they get to the right spot, what if we could literally construct our treatments molecule by molecule, building the perfect key for a very specific lock inside our own bodies? That right there is the incredible promise of nanotechnology. So, to really get this revolution, we first have to get a handle on the scale we're talking about. When we say nano, what does small really mean? Let's break it down. At its heart, nanotechnology is all about engineering matter. We're talking individual atoms and molecules to create materials that can do things they couldn't do before. And the name? It comes from the Greek word for dwarf, which is just a perfect way to describe this tiny, tiny world we're stepping into. Okay, here's the magic number. The nanoscale is basically anything between 1 and 100 nanometers. Now, to put that into perspective for you, a single strand of your hair is about 80,000 nanometers wide. Yeah, we are operating on a scale that is just barely bigger than a single atom. But here's where it gets really wild. This isn't just about making things smaller. When you shrink materials down this far, the fundamental rules of physics almost seem to bend. A material that's totally stable and boring in its normal size can suddenly become super reactive as a nanoparticle. Its strength, how it conducts electricity, it all changes, opening up this whole new universe of possibilities. So if these nanomaterials are so powerful, how in the world do we actually make them? It's not like you can just use a tiny hammer and chisel, right? Well, let's take a look at medicine's microscopic toolkit. Turns out there are two main ways to go about it. The top-down approach is pretty intuitive. You start with a big chunk of material and you just carve it down, like a sculptor carving marble. But the bottom-up approach, that's where things get really revolutionary. It's like building with molecular Legos. You assemble your creation atom by atom from the ground up. And what are we building? Well, let's meet a few of the key players. First up, you've got liposomes. Think of these as tiny, hollow delivery bubbles. They're made from the same stuff as our own cell membranes, which makes them perfect, biocompatible containers for carrying a payload, like a dose of medicine. Next, we have dendrimers. These things are beautiful. They're these tiny, tree-like structures, super small, less than 10 nanometers. And their unique branches and all the little spaces inside make them perfect for a controlled, slow release of a drug while it travels through your body. And then you have carbon nanotubes. These are incredibly strong, hollow tubes made of carbon atoms. They're a perfect example of how versatile these nanotools are. You can use them as a delivery truck to carry drugs, but you can also use them as super sensitive sensors to detect the earliest molecular signs of a disease. Okay, so we've got the toolkit. Now let's get to their most powerful application, turning medicine from a sledgehammer into a surgical scalpel with targeted drug delivery. Think about traditional chemotherapy, for example. It's a bit like carpet bombing. Yeah, it kills the cancer cells, but it also does a lot of damage to healthy cells, which is why the side effects are so awful. Nanotechnology aims to create a smart bomb, a treatment that hunts down and destroys only the diseased cells, leaving all the healthy stuff completely untouched. And here's how it works. It's so elegant. First, you hide the drug inside one of those nanotools, like a liposome. Second, you engineer the outside of that particle so it's like a key that only fits a specific lock found on cancer cells. Third, once it's locked on, the particle opens up and releases its payload. And fourth, the result is the drug's impact is maximized exactly where it needs to be and only where it needs to be. And you know, the benefits go way beyond just reducing side effects. As the research points out, because you're using less of the drug way more effectively, these treatments can actually become more cost-effective. And let's be honest, that is a huge deal for healthcare systems everywhere. So now let's see how these tools are actually being deployed on the front lines against some of humanity's greatest medical challenges, cancer and devastating neurodegenerative diseases like Alzheimer's and Parkinson's. Against cancer, the strategies are just incredible. We can use gold-coated nanoshells that latch onto tumors and then use an infrared laser to heat them up, literally cooking the cancer cells from the inside out. Or we can inject tiny glowing quantum dots that light up a tumor so a surgeon can see it and remove it with absolute precision. And maybe the biggest game changer of all,
using nanowire sensors that can spot cancer biomarkers from a single drop of blood, catching the disease at its absolute earliest stage. For Alzheimer's, one of the most promising ideas involves designing nanoparticles that are basically super sticky for the nasty amyloid beta proteins that build up in the brain. The idea is to create what they call a sink effect. These particles just circulate in your blood, pulling the harmful proteins out of the brain and letting your body clear them away. And with Parkinson's, the name of the game is precision. Researchers are creating these nano devices that can deliver dopamine, the very chemical that's missing, directly to the specific parts of the brain that need it most. That could dramatically reduce the awful side effects that come with current treatments. Now, I know this all might sound like it's straight out of a science fiction movie, but this is really happening right now. Just take a quick look at the timeline to see how fast this field has completely exploded. You know, the core idea was first floated by the physicist Richard Feynman way back in 1959. But look at the incredible acceleration after the discovery of things like carbon nanotubes in '91. Then the US government launched the National Nanotechnology Initiative in 2000, which just supercharged the research, and by 2011, we were officially in the era of molecular nanotechnology. What used to be pure theory is now very, very real. And this revolution is touching every single corner of medicine. We're seeing it in dentistry with nano-filled composites for stronger fillings, in surgery with flesh welders that use nanoshells to seal arteries. There are nanoscale ointments for your eyes, nanomaterials that help us engineer new tissues. It's even helping us fight antibiotic resistance. The impact is just staggering. Which really brings us to a final incredible thought. For the first time in human history, we have the tools to design and build our medicine at the exact same scale as life itself, the atomic level. We are standing on the edge of a brand new age in medicine. So the only question left to ask is, what disease, the one we all thought was incurable, will we conquer next?